All right, welcome to The Explainer. Today, we're going to be detectives. We're diving into the world of nanotechnology to solve a microscopic mystery that had scientists scratching their heads for years. It's a wild story that starts on a surface that was supposed to be perfect, and it ends with us questioning what stable even means.
So let's start with a puzzle. What if you could make something perfectly smooth, flawlessly clean, and then little imperfections just appeared out of thin air? It sounds impossible, right? But that is exactly the bizarre situation that researchers found themselves in.
Okay, to really get this, you need to know what we're talking about. We're talking about silicon wafers. Think of these as these super clean foundations that we build our entire digital world on. Every microchip starts with one, and they have to be pristine. Any little flaw, and the whole chip is worthless.
And here's where things get weird. Researchers would prepare these wafers using a process called ion milling. It's kind of like a hyper-precise sandblasting, but with individual atoms. And when they looked at their supposedly perfect surfaces under a powerful microscope, they saw these little blemishes, flaws that just shouldn't have been there.
Now, in any good mystery, you have your prime suspect. And here it was argon gas bubbles, little leftovers from that milling process. But there is a huge problem with this theory. The argon bubbles they knew about were a certain size, pretty big on an atomic scale. But the flaws they were actually seeing, way smaller. The sizes just didn't match up. It was the first major clue that they were looking at the wrong culprit.
So the case was already strange, but then something happened. A complete accident, really, that just blew the whole investigation wide open.
You gotta love this. A scientist takes a quick look at a sample, gets busy with something else, and just leaves the thing sitting in the microscope for a few hours. When they finally get back to it, whoa, there were more defects than before. They were literally appearing while the sample just sat there. Think about what that means. The flaws weren't just a one-and-done mistake from the preparation. No, this was an active process. They were growing, they were multiplying, seemingly from nothing. And that meant their prime suspect, the argon bubbles, absolutely not. Case reopened.
So the whole investigation had to pivot. If it wasn't the preparation process itself, it had to be something in the environment. The hunt was on for what was causing these things to grow. But what could it be? To crack this, they came up with a really smart experiment. Here's the plan. They prep a sample, then rush it into the vacuum of the microscope in under 3 minutes, so almost no air could touch it. Then they'd just watch it for 14 hours. After that, for the grand finale, they'd open it all up and let regular old air hit it for 2 hours. The goal was simple. Compare what happens in a vacuum to what happens in the air. And the results? Oh, they were crystal clear. This was it. This was the smoking gun they were looking for. Just check out these numbers. You start with a certain density of defects. After 14 hours in a vacuum, bam, that number shoots way up. We're talking a more than 7-fold increase in that first region. But then, get this, after just 2 hours in the air, it jumps again. So, okay, growth is happening in the vacuum for sure. But the air is like pouring gasoline on a fire. And when you see it as a bar chart, it's just so obvious. That first jump to the middle bar, that's the growth in a vacuum over 14 hours. But look at that last bar, that huge leap. That's what happened in just 2 hours of sitting in the open air. There was absolutely no doubt anymore. The air was the culprit.
Okay, so we've got our culprit, the air. But what about the air is causing this? Air is a mix of things. Well, the answer is a process that's happening all around us, constantly, even right now.
It all comes down to oxygen. It's a process called oxidation. The same thing that makes an old car rust. Oxygen from the air was literally reacting with the pure silicon, creating a flawed layer of silicon oxide. Mystery solved, right? Well, not quite. This still didn't explain the timing. Why was it slow at first and then suddenly so fast? And here is the final, brilliant piece of the puzzle. It turns out the preparation method is key. If you prepare silicon with chemicals, the surface is totally bare and exposed. It oxidizes almost instantly. But that ion milling process they were using, it does something different. It leaves behind a super thin 5-nanometer damage layer on top. Think of it like a tiny protective shield. So here's the grand theory, the whole shebang. That damage layer acts like a sponge. It soaks up oxygen, but it also slows down how fast that oxygen can get to the pure silicon underneath. And that explains everything. The slow growth at the beginning, that was just the tiny bit of oxygen already trapped in the spongy layer, reacting. And the super fast growth in the air, That was the unlimited supply of fresh oxygen from outside, finally pushing its way through the sponge to the silicon below. It all clicked into place, so the mystery was solved. But what they learned in the process ended up being way more important than just figuring out where some tiny spots came from. It revealed something profound about the very materials our world is built on.
This one number really says it all. The reaction is more than 4 times faster in air. It proves that the silicon surface, which we think of as this perfectly stable, almost inert thing, is actually in a constant, dynamic battle with the air around it. And it's a battle that the oxygen is winning.
So what's the big takeaway here? Well, this was way more than just a quirky little lab result. It revealed a hidden instability in one of our most important materials. And on a practical level, it taught us that you have to be incredibly careful with how you handle these samples. But the bigger idea, the one that really sticks with you, is that the surfaces we think of as solid and stable, they're not. They're dynamic. They're constantly reacting and changing.
And that leaves us with one last question to chew on. We solved this one tiny mystery on a silicon wafer, but it really makes you wonder, doesn't it? What other invisible forces, what other unseen reactions are constantly shaping the world all around us, just waiting to be discovered?